Rowan University, USA, Professor Yusuf Mehta. They will be taking today's lecture. We have two lectures scheduled for today. And after that, we have a tutorial session in which we will be having some hands-on practice, and sir will be showing us how their department and their center work there. They have a center named Creates here. They are working on a lot of projects and a lot of US government initiatives there. So today session, I think till now you have gained a lot of knowledge, as well as today you are going to get exposure about how the facilities in the Rowan University at the center for the Create, how it works. So I would like to welcome our eminent speaker for today's talk. Over to you, sir.
All right, thank you. Good morning, everyone. Today I have, there was a request yesterday about the mechanistic empirical payment design guide, and the original set of slides that I gave was a very shortened version of this expanded version of mechanistic empirical design guide. So I have now expanded the slides, and I'm going to explain this mechanistic empirical payment design guide in detail. This is the wave of the future. This is how, in my opinion, the payment design should work. It integrates a lot of pieces together. And there was a question yesterday if I would be covering MPDG, and I'm going to cover that in detail. Any questions before I proceed from any of the no audio? Somebody saying no audio. Hello? Can you hear me now or no?
Hear me? Well, I'm not hearing not here.
Can you hear me? You cannot hear us?
No. What purpose is?
Not.
Yes, now.
Now it's better? Now it's better? Hello?
Yes.
Okay. Okay. So I'm going to, just a minute, they're going to do some changes. So, you can hear me or not? Can you hear me clearly?
Yes, sir.
Okay, great.
Yes,
So,
yes,
okay. All right, great. So I'm going to start with material characterization and data input. And this is going to be very informative. I got these information directly from the Federal Highway and the U.S. Department of Transportation. I'm going to give you a brief history how this started. This no audio, sir. Again. What's right? Wait or now it is audible. Okay, great. Okay, so now I just want to give you a brief background. So right here, this project started in 1997, and this happened because people realized that the calibration factors that Asphalt Institute had developed, or the PCA method, is now not adequate anymore. Right? It was based on the Ashton road test. So in 1997, Witzak from Arizona State University got a large grant to develop this mechanistic empirical payment design guide. Now it's no longer called that. It's called Astro Payment ME. And he came up with a very comprehensive system to design payments. And it's not a design tool, it's an analysis tool, and I'll explain that in detail. But please feel free to stop me and ask questions as we go through this. This will be most of our AM. We will cover these slides in detail. So right here, looking at what I'm looking at, but there are a lot of pieces to the puzzle here. So here you are looking at unsoiled and unbound material. The soil and unbound material. You have AC and PCT payment, and then rehabilitation. Okay, so they are looking at a lot of pieces to the puzzle here, and we are going to address all of those today. Next. So we are going to talk about material characterization, analysis methodology, or what is the brainwork behind this new Astro Payment ME, and I think everybody will gain a lot as to this is the future of payment design, and many agents will eventually all over the world will eventually adopt this. So this is what it looked like long time back. These slides are the original slides from 2002, which is almost 23 years back. I can't believe it. So a long time back, and this was developed by Arizona State University as part of a grant. And let me explain. So they are now called ME Design Guide 2002, and now latest version is Astro Payment ME. So these slides are a little overdated, but the concepts have not changed, right? So and my goal is to explain the concepts behind this, okay? All the same thing and not yet the Astro. This is not yet an Astro design guide. It is not approved by the American Association of State Highway Transportation Officials, but every state agency is looking into it. New Jersey DOT is looking at Payment ME. We have an active grant with them looking at Payment ME as well. Okay, right here. This I have covered a long time back. Astro road tests are limited by scope and tests performed and conditions under which conditions were back in 60s and 70s. And this is what the roadway looked like, where the people drove, right? And the loop I showed yesterday, right? So one climate, Illinois, two durations, 2 years, 2 million axles, 50 vehicles, and then new construction. Some of these slides are covered from there. And this is very important. This is what was done, 2 million, less than 2 million easels. And then you have different projections. And now we are somewhere here. All the traffic that you see on heavy interstates or heavy highways in the US are more than 100 million easels. So we are way beyond the capability of the Astro design, which is less than 2 million easels. Okay. So that is why that led to the payment ME. Design methodologies based on experience, empirical. We talked about this ad hoc a lot. Statistical models and models of payment performance. Okay. Mechanistic empirical. It takes the payment performance, stresses, strains, and deformation, and then correlate it to field performance. And finally, mechanism. And this is the slide I have presented before. State of practice. Most of the industry in the world are looking at AI, PCA, Astro. They are here, right? So, and this is where the new payment ME is going towards the mechanics. We'll never be fully mechanistic. I explained that several times before. So we are moving in the right direction, where we are removing a lot of statistical analysis out, but you cannot eliminate it. All right, couple of things. Mechanistic empirical design, deformation, rutting, tensile strain, cracking, and this delta prevents rutting at the top, and this is the compressive strain to protect the subgrade, right? So you have that's the basic. Now I'm going to take my time and explain the concept behind this, right? So you have a structure here, okay, and you have a climate, okay. Okay, so now you have to assume a certain material and a certain section. It's a trial and design procedure. It's not like Astro where you get a fixed number. You have to input a certain number. Okay, so you have to input climate, rain. Actually, you can take weather data now. It's so sophisticated that you can put any weather data into the thing. You have to put the section, material properties, and you get the structure. Then you input the traffic. Okay, you have completely moved away from easels. Easels is gone. Okay, you are looking at axle load distribution through the entire blade. Okay, and so remember, if you have weigh motions data, that means if roadways have truck weights, that data can go in there. So easels is gone, EALF gone, everything, all empirical thing is gone. Then that goes into the elastic engine, that is the analysis. You get the mechanical response, you get the damage accumulation, and then you correlate with distress. I'm going to explain each piece in detail. This is very important here. This entire thing can be done by hand. By hand, literally by hand, which I did cover some of it. Remember the graphs I showed you, epsilon C, epsilon T, simple math you can do. So you can get the response anytime, and then you add the deformation. Today I told you, what is the time now? 9:20, 9:21, 9:22, 9:23. Now there are software. You can always add the damage, but you will eventually have to correlate statistically to cracking or rutting. Correct? Any questions so far? This is the basic concept of MVPDG. Let me explain. Now, if this exceeds the failure criteria, that means it is unacceptable, right? You restart the whole process. So you change your payment section, make it thicker, so on and so forth, and restart again. That's it. So it is a payment design procedure, but by trial and error. It is not a final number like Ashton 93. Oh, I calculate D, S10 equal to A1, D1, M1, A2, D2, M2. That's not like that. You have to give a trial number, predict the distress, compare. So if you now, the paid version of this is like close to $15,000, where it will optimize it for you. So like if you give your distress and all that, like it will automatically tell you what that is. Right here. Climate includes weather data, others, materials, asphalt, concrete, base, subbase, put it in the structure, and you keep repeating the whole thing, and you will get. So I'm going to cover this portion first. It accounts for a wide range of payment structure, new and rehabilitated. It still needs to consider overweight trucks. It can do that. Different material components, foundation, and existing payment as well. This is the Enhanced Integrated Climatic Model, EICM. This is what I explained before. This takes, I'll go back here, EICM takes the climate and the rain, and then EICM kind of correlates that to material property. That is what EICM, Enhanced Integrated Climatic Model. So I think I explained to you last couple of days. Oh, it is sunny today. It rained in the morning. What is the impact of that on the soil? Right, that is what is important. That there's an equation that converts all the weather data to all the changes in soil properties. Does that make sense? That is the EICM. Okay. So that is something at the back end it works. Includes NOAA, LTPP, USGS weather and soil index data. Material properties vary over design life. There is aging of hard mix asphalt, freeze-thaw impact of PCC. It is not only for asphalt, it is also for concrete. In fact, for PCC, this Astro ME is completely solid. So for Portland cement concrete, they have gone way ahead, and it is almost doing. It's doing very well. In asphalt, it is not doing as well because it's a lot more complicated material. Multiple acceptance criteria, distress and smoothness. I told you acceptance criteria. Can anybody tell me what is the acceptance criteria dependent on? When do you accept rutting of 1 inch? Is the failure criteria. What is the basic safety? Safety, correct. So remember, that is completely based on safety. Use the best available ME models, and then you have to calibrate for your own data. I've said that multiple times that every state needs to calibrate the data for their own state. So of course, this state has to calibrate for this particular condition. You cannot do it for Kashmir region or Maharashtra. You cannot do that. It has to be for this climate and this region. All right, let's look at this. 1993 guide had only one single value, right? A value, structural cohesion, reliability, S naught. You know all these numbers that we covered. In 137A, which is this current guide, there are 3 levels: level 3, level 2, level 1. There are 3 levels. Depending on how much money you are willing to invest, level 1 is the most sophisticated, level 3 is the least sophisticated. And I'll explain. Right here. Level 1 is project-specific testing. That means if you are going to do a national highway, you better invest, collect data from from the lab, go into the lab and collect data, okay, and measure the data. That's project specific testing. Everybody with me? Level 2, you correlate with standard tests, CBR, R value. That's another one. And level 3, look at national or default values. So that's number 3. So I want to explain this in a bit right here. I have to move this one. Right here. That's so right here. I just want to explain the input data. The input data level 1, level 2, level 3. I want everybody to understand that all of this will lead to E value. All 3 input parameters lead to modulus of elasticity. Okay. So if I am willing to measure resilient modulus in the lab, then it is level 1. So this is the most expensive, most detailed. Right? So that is project specific. Level 3 is default values. So if I give you soil characterization and I estimate the E value, then that is that. So all the 3 will lead to E value. E value is what goes into the payment design, like the Astro 93. Everybody with me so far? Like the Astro 93, E value is the most important one. Okay. So I just want to let you know that in the analysis, nothing changes. All the analysis uses E. So going forward, in the analysis, everything is the same. It's just that how you reach E value depends on how much money you are willing to invest going leading up to this. Is everybody clear? Okay. So that is what you need to look at. So let's look at this. Astro 93 had close to 5 flexible inputs, 10 rigid inputs. Now, any design pad has 100 plus total inputs. Completely different. The understanding, the ability to gather all the information and analyze it. Of course, the computational capability has increased too, right, from the 90s. So 35 plus flexible inputs, 25 plus PCC inputs as well. And I'll go through some of them. Input levels can be mixed and matched. So that means for the surface layer, you can use level 1. For the soil, you can do level 3. Doesn't matter. Remember, everything leads to E value. It's just that whether you have confidence in the E value or not. And then finally, damage calculation is exactly the same regardless of input values. Because all the damage calculations happen based on E value. So going forward, once you have a typical E value, you are good to go to do the design calculation. Why do level 1? Level 1 is the most expensive. As I just explained to you, if you're doing a national highway, you are doing a very heavily traffic road, it is worth the investment. You cannot stop traffic again and again if you do a poor job in designing the roadway, right? So you have to do lab testing of all the layers, right? You have to do resident modulus or whatever it may be. Measure traffic, detailed traffic, what trucks are coming. So more data you put into the parameter input, the better is going to be your design. Okay? So material properties, and then there are many pieces of material properties, and then you have damage accumulation as well. Material characterization. What is needed? Modulus values. We keep talking about modulus time and again. That's what you need finally, right? And then the thermal properties as well for concrete. Why it is needed? To calculate stresses and strains, right? So that's what leads to the distress, right? Tensile strain leads to fatigue cracking, deflection at the top leads to rutting, so on and so forth. And thermal property, that is how modulus changes with water, temperature, so on and so forth. This is the most important. Design life is divided into increments. Specific material properties, traffic and parametric data. Okay, I'm going to explain this. I do. This is the brainwork of the Ashton 93. The entire 20 years, I want everybody's attention, if you can, on the board. So the entire 20 years, okay, 20 years in the MEPDG is divided into 15 days, 15-day increments, half a month, right? So you can do the math, right? So 24 times 20, 480, correct? So this, each box is 15 days. Everybody understand that? Okay, now, in that 15 days, there is an assumption made, nothing changes, which is a fair assumption for a 20-year period for payments, right? We're not developing a nuclear reactor, right? So, having said that, in that 15 days period, in this block right here, you are going to assume the traffic is constant, does not change. That means my daily traffic is consistent over the 15 days, right? Material property is constant and environment is constant. Which is, and when I go 15 days, it changes. But somewhere, if I make this 15 days into 1 minute, you can imagine how long that computer program will run, right? So the more tighter I make the time, the longer it will run, right? But time is money, right? So if I run this program and I sit there for 5 hours, nobody will use that program to get the first iteration. Remember, it's an iterative process. So they have said, okay, I will minimize my risk and minimize my losses, and I'm going to take everything in 15-day period, and I am going to assume that everything is constant over the 15-day period. What is going on? Yes. Right here. Profit is accumulated over time. Okay. PCC modulus remains the same. Now I'm going to spend some time on this graph. This is a very solid graph over thing. This is that 15-day period I told you. One slice of that entire puzzle. Okay. I want to remind you that entire 15 days is repeated every year. Like you do 15 days over 12 months, correct? That is repeated 20 times, right? Unless you have a very good reason to believe that from year 1 to year 2 there is a change. You have a model to predict that there's actual warming happening. Actual precipitation is going up. Can everybody understand that? So once again, I divided everything to 15 days and then everything is repeated every year. Got it, everyone? So let's look at this. This is very, very clear. Traffic is accumulated over time. That's your cumulative growth traffic, correct? Everybody with me so far? So you can't design only for the 8th year. You have to design for over time. Next. PCC is very simple, right? PCC modulus remains constant. Right. Let's look at the subgrade modulus. Look at this here. We covered this before. This is 1 year, 0 to 1 year. Correct? Right here, freezing January, very cold. This is typical US. March comes back up in December. Can everybody see that? So this is the data that is collected for 1 year and it is repeated over the next 20 years. Can everybody see what this is going on? The subgrade modulus is changing with time with the freezing and thawing. Look at the granular based material. January, February, and because this material is more permeable, the modulus drops, picks up, and you have a cyclic behavior. That means somebody has to invest money to calculate this first year. If it is project 1, level 1, you spend the money and test it. If it is level 2 or level 3, oh, you know what? It's a local road. I don't want to invest money. I will go to assume some data. Fine. Right? Depending on where it is. Let's look at asphalt modulus. January, very cold. Come back to summer, very hot. Asphalt is very, very soft. Modulus is very low. Come back up, goes down. You got it? Everybody with me so far? This is the framework of MEPDG. You have to only put for 1 year. Everything automatically gets repeated for the next 19 years. Everybody with me so far? For 1 year, you input traffic. It takes the entire climate data automatically, weather data, and converts that to water content, temperature for 15 days and keeps it constant. Everybody understand that? Any questions online as well as I'm going through the concepts? All right here. Rut depth, longitudinal, thermal cracking, IRI, fatigue cracking. These are the final field performance, right? You will never be able to match it. You have to eventually use statistical correlation to relate that to this thing. Thermal cracking happens at low temperatures. How does thermal cracking happen? Remind me. How does thermal cracking happen? When does it happen?
Very less temperature.
What is it?
About 32, minus 30 to 40.
Yeah, so if you have a cold front, remember, do not confuse thermal cracking with freeze-thaw. Please don't confuse that. Then you have rut depth, and then launch cracking can happen. Oh, this is the crack. This is in the wheel path, right? And you can see this crack along. And you know, one of the times I said, due to the tire treads, it can happen right in the wheel path. You would see that. Next one, rigid, right? You have transverse cracking. You have punch outs. Remember I talked about in CRCP, if you have too much, you have CRCP, you have joint faulting, and then you have roughness. IR, that's also there. So again, it is an asphalt and a concrete design, right? Very, very comprehensive. Any questions for me online or here? All right, allows design of new pavements, composite pavements, and rehabilitation. I want to go back and explain one thing right here. So right here, you have one load coming in this 15 days. You have, what happens is, let's say I assume a design. Remember, you have to assume a structure. Okay. I assume the 3-layer structure, E1, E2, E3. Okay. Remember, you have to get to key value. I said that multiple times. Either it's level 1, level 2, or level 3, you have to get the key value. This is what happens. You apply the load, right, at that particular time. You calculate rutting, tensile strain. This is delta. And then you calculate epsilon C. Correct? You do that for the first 15 days. Remember, you do that, you keep it constant. Then you calculate delta 1, epsilon T1, epsilon C1 for the first 15 days. Everybody with me? Now the next 15 days come. Add them up. Another 15 days come. Add them up. Add them up. Everybody with me so far? That's exactly what this is. This engine that it is saying, right here, this is a linear elastic engine, calculates the response. It is this that we did in the class, right? You can calculate stresses and strain. That's what I covered is so powerful, because this is, now you might think, why elastic analysis? Because it is very fast, right? If I do viscoelastoplastic, it will take me 2 years, 3 years, so 2 or 3 years, I'm saying, 2 or 3 hours. Right? So that's why they did elastic deformation and so on and so forth. And now you add them up. Damage accumulation that you see this graph is this summation. Delta 1, delta 2, delta 3, delta 3. That doesn't make sense. I want to make sure I clearly explain all the pieces of the puzzle very clearly. How you get it. You should not have any doubt, how do I get this number? Now, at the end of 20 years, let's say this number turns out to be 0.2 inches. Alright? This has to be calibrated. So after calibration, it will work. Now, if your criteria is 0.5 inches, that's your criteria. Correct? Are you good? Yes, you are good. If you want to make it less expensive, you will change the structure. Right? Otherwise, you're good to go. If this number turns out to be 0.6 inches, and your criteria is 0.5 inches, you change your structure. That's really fine. Does that make sense? Good. Any questions online or here? As long as you understand this, everything is very straightforward. Where this thing is at, yeah.
That's for 1 year.
And you repeat.
Repeat for whole 19 years.
Yes, whole 20 years. Correct. Next one. Yes. So that's why it is very important that now the results come out. You can do batch analysis. You can put multiple sections, and now that algorithm runs for like optimization. Because remember, you can also now put cost. So I'm not even included cost in this argument, right? This is purely a technical discussion. So yeah. Go ahead. For 1 year, correct.
Data will be collected for each 15-day period for 1 year.
Correct. Absolutely. You want to collect for every 15 days for 1 year and assume that 1 year is not going to change over the next 19 years. Is that clear? Question for me? Where did I go? Right here. All right. You can see that you need structural design, material selection, traffic and climate, and construction. All the pieces have to come together, right? So I'm going to explain that. And so all the pieces, I think I mentioned to you that different agencies don't talk to each other, right? Geotech group doesn't talk to structures group does payments group, and payments and concrete group. But you cannot have this E1, E2, E3 in one payment section if everybody don't talk to each other. Does that make sense? So if you don't have soil data, people talking to the payments people, they can't input the number. Correct? So soil people need to talk to each other. The whole public works department has to change their way they do business for this to work successfully. If the geotech group, oh, this is my division, don't talk to me, then who will put the input data of the soil? Does that make sense? So this is more than a technical problem. It's a more of a cultural problem and so on. This is very old data set, sorry guys. So that's fine. 8 megabytes on that. But right here. This is what the screen looks like. Right? Does that make sense? A design guide. And it has changed over time, but it is fine. They're like that. So you need to have monthly adjustment, vehicle class distribution, hourly class distribution, traffic growth factor. Remember the G, right? So everything is there. The concepts are there from the earlier, right? It's just that now the distribution is much more severe. Then the climate. This is the beautiful part. You can take the climate data directly the weather data and input in there, which is beautiful, right? And then you have drainage, surface layer, layer 1, layer 2, all of that. Traffic design, you have monthly adjustment, vehicle class distribution, hourly distribution, right? And then traffic growth factor, axles per truck, you can put all of this. And if you have, this is designed for the US system, of course, but there are, I think in New Jersey, there are 20 locations, which gives you the axle load distribution for 20 locations in New Jersey. You can directly input that here. So that gives you that. So this is the concrete one, right? Material is JPCP. PCC layer is 10 inches, right? Unit weight, concrete 150. Poisson's ratio, it has range given to you. Coefficient thermal expansion and contraction, stakes will be considered. Thermal conductivity, and so many of these. Now, I just give you a small tip with in concrete, the most sensitive parameter happened to be the coefficient of thermal contraction. We discussed this last time. Thermal expansion contraction is a big problem in concrete. And they did find that in the MEPTG as well. Click on the input parameter, so and so, it gives you the expansion explanation as well. And that's what the parameter looks like. So look at that project information, traffic, climate, structure, you can put that and you run the analysis, right? So it will plot everything, all the numbers, crack depth, surface down, bottom up cracking, thermal cracking, crack depth, all of that will be plotted. But the framework is here. This is the black box. So you can imagine the risk I feel if I gave this to my new engineers and they use this program, it is like a toy. Believe me, it's like a fun toy. You put something in, it will spit something out. But do you have the knowledge to understand, interpret data? Does it make sense? Does it make logical sense? If I told you that, can you optimize it for me? And if you don't understand the fundamentals, you will struggle, right? It's spitting out what you input, right? And it has got set models. And always softwares make me worried because students become intellectually lazy. You know, that's just, I would become that. You know what I mean? And I'm very much afraid of that. This is the one. Look at this. I'm going to explain this in detail. Faulting, this is concrete, and over 20 years of time. Okay? And there are two numbers there. I'm not sure if they explain the two numbers. Oh, yes. Right here, 0.16 is the agency performance criteria. Okay? Due to safety. Right? So, if my difference in the slab is more than 0.16 inches, then it is unsafe. Everybody with me? So, now there are two numbers. One here and one is here. Okay? I'm going to explain that. I'm going to make sure the slide don't cover it right here. Okay? This number below is at 50% reliability. I am taking 50% risk. That means if I analyze this data, if I construct this payment, there is 50% chance that I will not, in 20 years, I will not reach this number. Got it. This is 90% risk. That means what it is doing is, it is telling you that if I only take 10% risk, this payment will fail in 14 years. That means you will have to make it thicker. I will repeat, right? This is 50% risk. And at 50% risk, this payment is fine. It did not reach 0.16 in 20 years, my structure is fine. But I'm worried. It's a heavy road, 90% risk, reliability, I apologize. 95% reliability, 5% risk. Now, suddenly it will multiply this prediction by a certain amount and it will say, okay, 15 years I have hit the failure. So at 95% reliability, this structure will not pass. You will have to redo the analysis. Can everybody see that? This number depends on the agency. Whether the agency wants, because it is cost. It is cost, nothing else. Does that make sense? There is the only magic here is this is a multiplying factor when I increase the reliability. Can everybody see that? Questions for me? Any questions online about this?
Sir, about the thing on the board. Yes, sir, was mentioning about the calibration.
Yeah, you don't calibrate. I was not talking about the calibration. So there is no calibration. I was just saying that calibration is already done. So if you have 0.2 inches is added up, right? And if your performance is 0.2 inches and the criteria is 0.5 inches, not that. I assume the calibration is done. I already explained that, right? It assumes this model is already calibrated. That means I'm doing okay. My prediction is less than the criteria. My payment is fine for rutting. It may not be okay for cracking. It may not be okay for IRI. But if your performance is 0.6 inches, then you have paid the section and you have to redo the analysis. So I did not talk about calibration. I'm assuming that you know that process already. Does that make sense? But you have to calibrate eventually. Does that answer your question? What is it? Something else in there? Yeah, that's the thing. Right here. Did everybody understand this? Let me explain one more thing since the mention about calibration. We calibrated, Rowan University creates calibrated for New Jersey DOT for fatigue cracking in 2008-2010, this model. We had to assume no factor of safety. So always calibration is done at 50% reliability. No factor of safety. Then automatically, if they would choose to apply a factor of safety, they can. But calibration always should be done at 0 factor of safety. Then eventually you apply the factor of safety. So at 50% reliability, You calibrate the model and then you move that up. Next one. Rutting. This is, you are looking at each of these shapes here. Can you guess, looking from this, which one is asphalt, which one is soil, which one is subgrade? These are independent ones. The one of them is each layer, and the top one is total. The top one is a summation of these three. One is subgrade, one is base, one is. Can you look at the shape and tell me which one is asphalt?
Magenta.
Which one?
What? From magenta.
This one? This one?
Pink color.
Pink color. Let's look at this. Look at the shape of the blue one. Can you see flat, bump, flat, bump, flat, bump? Summer months, you see bump and rutting. Then it becomes flat. Summer months. So the bottom one is asphalt because you see flat, bump, flat, bump. This one is subgrade, another is base. Got it? And this is total rutting.
What of the asphalt on the top of the layer? The rutting is maximum.
Not necessary, friends. Not necessary. Depends on what the section you select. Right? Does that make sense?
But rut depth is maximum will measure the asphalt level. And at bottom layer, the deformation will be reduced.
If everything is correct, logical, right? But you could have that your base, and there's another problem to this thing, which I'll come to this, but I'll answer your question. Subgrade and base could be a lot weaker. Possible, right? So subgrade and base could be a lot weaker. That could cause rutting in the lower layer, right? And asphalt to be. That's to answer your question. So yes, logically it makes sense. I'm closest to the surface, asphalt rutting will be more. But let me just explain. This was the biggest flaw in payment ME, is that they could not have enough data. Remember, I asked you in earlier classes, if I see rutting on the surface, I asked you this question: how will I know where, if I were to be very thorough, where the rutting happened? What will I have to do? I asked this question earlier. So rutting happened on the surface, but I want to exactly know assumptions. I want to exactly know where the contribution was rutting happening. Right? Does that make sense, everybody? So the top is 0.5 inches, let's say. But it could be 0.1 from here, 0.1 from here, 0.1 from here, 0.2 from here. Everybody with me so far? But if I want to exactly know what it is, what do I need to do? Anybody online, you guys? If I exactly want to know, what do I have to know the exact number? Yeah, I have to do a cross section. You are 100% correct. You have to cut the pavement and exactly measure that. Correct? When with Zach, he passed away a couple of years ago, he asked and begged state agencies to give me this data. Everybody refuses. So I'm not going to cut a hole in my payment, right? Because of your study, because it's a cost. So he could not get data, rutting data for lower layers, exact data at all. He begged for them. This is a US government grant, state of New Jersey, Rhode Island, please contribute, give me the data. No, we will not cut our payments. What did he do? He did this. He had to do something. Correct? He had to do something. So he said, okay, total rutting is 0.5. I'm going to proportion the rutting to the thickness of the layers. So he did some funny math. In the absence of any data, he said, okay, if this is 4 inches, 3 inches, I'm just giving some examples, 4 inches, 10 inches, and so on and so forth, I proportion these thicknesses, rutting by the proportion of the thicknesses. He had to do something, some logical answer. Therefore, he eventually said, this number is bogus. That is to answer your question. He admitted, like, I had to give me, but please don't use this data. I was forced to, so all the writing was kind of locked to 0.3 inches. So this will support your point that it's happening, but this was a flaw of his calibration process because he did not have the data. So there's so much to learn from to do the study right. The amount of data needed is so important. So from now on, MEPDG says not even try to worry about the lower data set. Forget about it. Fair enough. So nobody wants to invest the money. Does that answer your question? Did I answer all your questions right from this point? Verify against agency criteria. We talked about that also. That depends on the. How did this fit into the FHWA national program? Payments that meet our customers' needs and are safe, cost-effective, longer-lasting can be effectively maintained. And then demonstrate benefit, a link between structural design, mixture behavior, and material characteristics. So we are going to talk a little bit more about that as well. It was created for the Office of Infrastructure. So right now it has gone to ASTRO. A division of ASTRO is approving it. But Federal Highway for 10 to 15 years took on the whole thing of educating the whole industry. They call it a design guide implementation team. That's what they called it. And these were the top, and these are very old, which is fine. 20 years. Remember 2002, it was developed 2003, right? Are you guys born at that time? No? Right. All right. Sounds good. So right here, New Jersey was one of the pioneering states, right? So these were the pioneering states. All right, let's keep. Oh yeah, so this is so right. So now some very interesting data I'll show you. Field section for both unmodified and polygon mixes PG 76 and 7622. Two sections failed 5 inches in thick in fatigue cracking and grutting, and they did some testing. I'm going to show you some data. Okay. All right. I have 9 minutes. Yes. I'm going to go to the next set of slides. Any questions from me? This is if you guys step back from ASTO, structural number A1, D1, A2, D2, and look at this day and night, right? Just the amount of leap the industry took, right, from A1, D1, M1 to this information is truly, and I, as a researcher, I have to tell you, it's when you are given a blank slate and you're doing a design, any of all of you grad students, it's very challenging, right? People from outside always have a written paper and they're very easy to criticize, right? ऐसा करना चाहिए, वैसा करना चाहिए, ये करना चाहिए. But you sit in the problem when you have an empty slate and you have 10 options in front of you, right? Such a high profile case, everybody's watching, everybody's like a wolf, right? Like everybody wants to say that they are smarter than the other. Like I could have done it better, but you are not the person who got the grant, right? So I have such appreciation when people develop something. It comes with the honest constraints, and people complain about the constraints, but people don't understand that each constraint I remove is 2 more years of work, right? Any parameter I add in that equation, somebody is going to ask, what is the impact of that parameter? That is some grad students 2 to 3 years of work, right? Everything else, because I want to give that perspective and appreciation. When you guys see these equations, it doesn't happen just like that, So I also get upset when people just randomly criticize research without understanding, like, when you gave me this problem, I had 10 parts. I have only X amount of budget, Y amount of years. I don't have my full life. I had to use my knowledge, my brilliance, my technical expertise, my expertise of the team to come with one part. Did I make a perfect decision? Maybe not. But I made the best intellectual decision at that time. And you know what I mean? And it's very important that everybody understand that very clearly. You know what I mean? I'm going to start with soils first, and then I'll go to All right, let's keep going. Soil and unbound material, then I'll go to asphalt. Discuss general soil properties, understanding of design and analysis. Like a classic example is this, right? Right, rutting is a classic example of soil. Everybody was criticizing him. But come on, right? Like, if you don't give me good data, what am I going to do, right? So he had to, people were like, oh, it's imperfect. Everything is going to be imperfect, right? All right, here. Input parameters, soil input, asphalt is resident modulus, PCC is modulus of substrate reaction, K value, this has to be adjusted for climate and what I told you that multiple times, and then K value also have to be adjusted for that. Again, use the linear elastic or finite element engine, that means stress frame as well. Okay. This is right here, level 2 and Julia or Jacob Uzan linear elastic analysis. Jacob Uzan is a researcher from Israel, from Technion University, a brilliant man in modeling. And right here you have a Winkler foundation. You saw the springs that I drew, right? So you have to get the K value, E of the base, and then the concrete, right? So simple concept. And then you have the modulus values. Natural default values, right? Now, if you want to not measure, you don't want to measure soil properties, you can take soil classification. So the entire country, Government of India has the soil classification of the whole country. So you can take by soil, because I've all done soil classification, like CH, CL, and all that, ML, so all the soil classification based on gradation, PI, liquid limit, plastic limit, all that. So you can estimate your A1 through AM, you can use the soil classification, and you can get the modulus value. So if you don't want to invest money, it's a local road, I don't want to do MR testing, which is very expensive, I can just use this classification. But remember, look at the range, 38 to 45,000, okay, I'll assume 40,000. Fair enough. And at the bottom, 33, 38,000. So if I don't want to test the money, remember the final value is what? Modulus. I have to come to modulus. E value is the final. I need to come from either place. Level 1, level 2, level 3, I have to come to E value. Next one, level 2 soil properties. You can now use CBR, R values, layer coefficient. You can use it in the past, right? After 93. Plasticity index and gradation and dynamic cone penetrometer DC. Right here, these are some of the equations. If you did CBR test and California bearing ratio test, you can use this equation. If you're using MR, you can use this equation. So this is the, what is R value? Drawing a blank. CBR is by DCP, so you can use any of these to get the final MR value. Okay. There's another question. Oh, okay. Oh, okay. New HMA payment, laboratory resident modulus, rehabilitated FW deflection. I explained that yesterday. 7 sensors, you get the MR. So that for level 1 is FW deflection. That means you have already existing payment. I want to know what the condition of the existing. I have to do FW. And then level 1, you have to calculate resident modulus. I explained that in details a couple of days back. Level 1 not included in the new PCC. Soil behavior under repeated loading, represents field conditions, define stress strain relationship. So this is already covered before. This is the deviatoric stress versus the resilient strain. It's good to get a little review. It depends on the recoverable of the resilient strain. There is permanent strain, but by definition, this ignores the. And then we talked about this. I don't need to write this again because this is sigma D over epsilon R. I covered this. Test soil is in elastic state, depends on the confining pressure, depends on the load. Remember, I talked about granular material and cohesive material. And this is the equation if theta normalized to the atmospheric condition and shear. Remember, if it's a combination, this The top part, the first part, the theta is only valid if it's completely granular. Remember stress invariant. And the last part is only valid if it is cohesive, shear, or sigma deviatoric. It's a combination if material is neither fully cohesive or neither fully cohesive, which is most of the soil, right? I showed this graph before. This is better graph. Right here, you have 2, 4, 6. That is your confining pressure. And then you have this 4 down. Confining pressure dependent is K6, sigma 3, right here. And then load dependent, sigma D dependent is there right there. Intercept is K1. So you have K1, this is right to the intercept, K5 is the load. This is how you get the problem. History of the test procedures, there are many. 1999, resonant modulus, and then there are other ones. Yeah. Yes, correct. It is the octahedral shear stress. That's right. That is tau octahedral is the same as the sigma deviatoric divided by 2. So that is correct. So octahedral shear stress is the same thing. So if I do simple Mohr circle, you guys did all Mohr circle? Everybody did, right here. It has been a couple of 100 years since I did one. So right here, so you look at the Mohr circle, right? And then you have your sigma, this is your tau, right? And that's your principal stress, sigma 1, sigma 3. That's your sigma D. Your tau external is sigma D over 2. That's your Mohr circle as well. Yeah, that is correct.
So she's asking, what is octahedral sources?
Oh, octahedral. Oh, it's been a while. In this octahedral, I don't know the exact. It has been a long time since I did the definition of octahedral, but it is. I think in this case, it is straight tau is equal to sigma d over 2. But I don't remember offhand. You just have to look at the definition from somewhere else because I don't remember offhand what it means. I think it is accounting for all the other all the 3 test traits. So it can be, I think if I remember octahedral, you have to subtract all the stresses. I think it is something like this. I'm not 100% sure. I don't remember offhand. I should stay away from assuming anything. So these are like the difference in stresses or something up to this level. Is tau octahedral stress. But
one equation.
This one.
Yeah.
Yeah, so that tau octahedral in this case, like it is accounting for all the differences in all the principal stresses in each direction. So I think that is what the it's a very generalized equation, but in our case, tau will be sigma d over 2 because the confining pressure sigma 2 is same as sigma 3. So this will kind of drop out, and then something like that, and you will get your sigma d.
So was it anyway related to the stress invariant?
No, it is not related to stress invariant. Tau octahedral is directly related to deviatory stress. So tau octahedral is, in our case, is related to deviatory stress. It will be right. So confining stress. So they are independent. So they are two. That's why they are in two different equation slots. Yeah. All right. So now internal and external measurements needing static compaction, loading sequences, and then that's your confining pressure and so on and so forth. Right. Use one test procedure. Strictly define the sample pressure in certified lab equipment. So consistency is very important. Everybody does the test in their own way, get garbage data, garbage input in the MEPDG, and you have a fun. Moisture adjustment. That's your EICM. This is what I was talking about. You have to account for, this is optimum, and you have to account for moisture and freeze thaw and change my resonant modulus due to rain and so on and so forth. That's the environmental factor. Total resonant modulus at optimum when using EICM. So you have to test the in situ conditions. There's some questions coming up here.
That campus.
Okay, everything good?
Okay.
Okay.
वहाँ से रोटेट कर दे ऑटो रोटेशन बना दो ऊपर से स्लाइड ऑटो रोटेट नहीं रोटेट ही वो ऑटो रोटेशन ऑन कर दो
Yeah, very good question is that the payment design models were developed, and what was the need to improve this MEPDG model? Correct. I mean, not the MEPDG, the mechanical empirical asphalt institute model, right? So what was the need to do that, and why was the need to calibrate? So I want to clearly tell you that the asphalt institute at that time was the state of practice, state of art at that time. However, as you can imagine, that they were done based on very limited road tests. So there were failures. There are constantly failures happening. People are seeing that as new mixes are developed, as new designs are developed, soil properties are different than the design. So we, as in the US, we ask every state to calibrate on a continuous basis. If you do not calibrate at a continuous basis, you are going to see premature failures. So you are asking for reports. The reports usually will not come out regularly because it is more on the working side of the industry, right? So if a payment fails for a particular state, they go back and check, okay, what were the input parameters? Why was it incorrect? And then they initiate a research project to kind of fix that problem, you know? So to answer your question, yes, the payments have been failing in the US and across the world, and that was the need to develop this payment design. Will this design methodology solve all the problems? Of course not. Right? It will not solve all the problems. If they solve all the problems, I'm out of the job. Right? You know. So it's interesting to know that every agency needs to be vigilant and have to collect performance data, collect all the material data, and calibrate the model continuously. Right? That last piece from stresses and strains to distresses is always going to be empirical. And if you do not collect data on a continuous basis, the models become outdated very fast. You know, so I hope that answers your question. It's a very good question, but it will be hard to get data unless there is a national study to do so. Okay, so right here, I'm going to keep going. Here is looking at soil properties. We are looking at optimum versus equilibrium with time for fine grained and then for coarse grained materials. And then resilient modulus, you are looking at equilibrium days of coarse grained, and you can see resilient modulus kind of flattens out. Okay, right here, freestyle, but we have seen this graph so many times. You have October to January, and then you have, this is the soil properties right at the bottom, right? And then you have a frozen state, right? And then you're thawing. This is when you have, the thawing, that's when you have the most damage happening. We talked that in the UF, right? And then you have water slowly released at the equilibrium state. So that is what you're looking at freestyle this minute. And remember, I told you for the entire year, you will take 15-day data, right? And that's exactly what so this is 1 year, it is repeated for the next 20 years, correct? I'm just reminding you what I just said before. And you will pick up 15 days of each data set and you will assume it to be constant. So it will be like blocks of 15 days. Does that make sense? Soil adjustment, plasticity index, gradation, and GWT. What is GWT? Quantitative, great. Specific gravity, maximum dry unit weight, optimum content, and hydraulic. Very good. Again, summary, levels of input, level 1, level 2, level 3, all need to e-value. Design the guide analysis of soils, you have to do moisture adjustment, freeze-thaw adjustment, and resilient modulus testing. Geotechnical aspects. We are at 10:15, do I have time?
So we have well,
Okay. I'll go to soils. Any questions? Any more questions from the? I'm getting some great questions all over. I don't think I'll be able to cover the whole thing until the break, so I'll go some of them. Then we can take a break and come back to this, right? Right here. So this is the asphalt and then I'll try concrete asphalt. Flexible pavement design. So I covered the soil. Now we are going into asphalt. This is a new methodology. We're talking about test and equipment, new construction design example, and sensitivity of asphalt. Mechanistic empirical methodology. Once again, 1993 Bayer coefficient and structural number. That's the only thing that. Right here, MEPDG, you have a dynamic modulus or master curve, which I will explain, and then Poisson's ratio. Okay, two things that's important. Analysis model. What's new in flexible pavement design? You have layered elastic analysis, right? You have to do layered analysis because of speed, right? Otherwise, this becomes very low. You are looking at stress-based on methodologies, top-down and bottom-up cracking. Top-down, remember I told you causes fatigue cracking, and here is the very classic example of, like this is like almost like a priceless code where you know where the damage happened, right? And you can analyze that as well. Rutting and thermal cracking. I explained all those distresses in detail before. And then overall performance IRI, and then that relates to PSR. Compatibility with the new superwave system, and they do superwave here. Do they do superwave here? Superwave? No, they do. Okay. And then they do rutting, fatigue cracking, and low temperature cracking.
So one question.
Yeah.
There is a seasonal change in E in subgrade. How we will incorporate this change in modeling and a pavement design, which is what I'm asking.
Is a seasonal change. This is not the reason. Right here. So just to answer your question about the seasonal change, what you will have to do is, if you have seasonal change within the year, right? And we just explained this. So if you have this happening, right? We just saw this, right? Right? Over the 12 months. Okay? So this is January and this is December. Correct? So what I have to do, if I want to do seasonal change impact, as I told you earlier, you divide this in 15 days. Correct? So January to February, now you have 2 data points. Correct? So I have to take MR of the first part, MR Jan 1, MR Jan 2. Correct? Fair enough? So I have 2 numbers. In this case, it is constant. In your case, it may not be constant. Okay? So now you have to take this resident modulus of the first part, and I have to take of the subgrade, subbase, base, and hot mix asphalt. Of the first 15 days, you have to take all the properties for the first 15 days of January. As I told you earlier, you will have to keep it constant for the first 15 days, right? Now you have traffic for those 15 days. You put this in your linear elastic analysis. So you have MR of J1, right? E2 of J1, J1 in January first part, E1 of J1, so on and so forth. So you will get delta 1 of the first part, epsilon T of J1, epsilon C of J1, so on and so forth. Then your J2, F1, F2, so on and so forth. So you will have 24 data sets, and you will have to add them up, and you will get for the first year, and you keep repeating. Does that make sense? That's how you account for the seasonal, because now you have accounted for the change along the year. Does that make sense? So that is how you'll account for seasonal changes in the within the year. I hope that answers your question. Okay, let's look at this. Right here, you will look at dynamic modulus and tensile strength, thermal contraction, and you put in the linear elastic analysis, which I just explained to you. That is your linear elastic analysis. This is good timing. So right here, you have the payment response, and that is this delta 1, ET, epsilon C. That is your payment response for each of those days. Then you keep adding them, and then you have another. Dynamic modulus, I'm going to cover that in detail. That will be a new concept for them to do different time condition superposition. So we will do dynamic modulus E star, simple performance test, mixed volumetric process level 2 and then level 3. This top one is for rutting and fatigue cracking. Bottom one, tensile strength, is for thermal cracking. By now you should know what each one is. Rutting at high temperature, fatigue cracking at intermediate temperature, and thermal cracking at low temperature. And then we will correlate with default values from LTPP, E star, tensile strength, speed compliance, and then finally layer coefficient, and we will use it in the hot mix as well. New HMA payments, we will talk about dynamic modulus, dynamic shear rheometer, and I can do some discussion about material properties as well as within the context of the mixed design. Direct properties, binder volume, gradation, and total unit weight. Right? Shear modulus, binder shear modulus, I think your student is measuring in DSR, right? Dynamic modulus ER, ABTS, phase angle, and Poisson's ratio. So if you guys are not aware of this, I can explain. Fine. We can start this later.